Hello, everyone. Thanks for showing up here. My name is Yuhao. I'm a final year PhD student advised by Professor Arun Kumar at UC San Diego. My main research interest is in machine learning systems. That is to make machine learning and data science easier and faster. This is our work called LOTEN. First, let me give you a one-slide summary of this system. What is it? LOTEN is a scalable distributed graph neural network training system. Through this work, we try to bridge the gap between existing graph analytical systems and GNN workloads. The main idea is to decouple graph processing and neural networks for separate scalability, and our experiments showed that LOTEN is indeed the most scalable system among the ones we tested. Before we get into it, first is a bit of background. You see, lots of data are naturally represented as graphs, and various applications exist. For example, we have social networks, biochemistry graphs, and citation networks. The applications range from low-level tasks such as node classification and edge prediction to high-level tasks such as drug discovery, social science, and recommender systems. To better understand these data and tackle these application tasks, we must model the graph data properly. That includes modeling both the graph structure and the properties of these vertices and edges. The scale of these graphs could also vary a lot in reality, causing many scalability challenges in graph processing, as we will see. On the other hand, deep learning has also been applied to graph data in the form of graph neural networks to solve various application tasks. Here is a quick rundown of it. This is a typical GCN that takes in a graph with node features and outputs an embedding per node that is a numerical representation of both the node features and also the graph structure surrounding a node. I have a data flow diagram here to illustrate this. Starting from the graph features, they are first fed to a message function. This message function sends messages to the neighbors of each node, depending on the graph structure, obviously. And on these nodes, an aggregation takes place. And then the aggregated messages are fed to an update function before we can get a new set of node embeddings. These three functions are the core of any GNNs, as they can be neural networks, hence the name graph neural network. And there could be multiple layers, and we get updated embeddings after each layer until we reach the very last layer, and we get the end embeddings, and we can use them for our downstream tasks. It turns out GNNs are very challenging workloads to handle for the underlying systems, and they can be very difficult to scale for a few reasons. First of all is the complex data access pattern they have. Say, if we tabulate all the data in this table, if it was just regular deep learning and minibatch SGD, we could just scan through the table iteratively and we batch them. It's very simple. However, with GNNs, we actually end up with these semi-random reads. It's scatter pattern to be precise, which depends on the input graph structure, which is very hard to predict, followed by these sequential writes. This is also very different from the regular deep learning data access pattern. And the problem becomes even nastier if our data is partitioned, say, if I have multiple nodes. Then the GNN would incur almost all-to-all communications of these dense vectors across our computational nodes. And needless to say, it's very expensive and brings in heavy overheads. Next, we also have the scalability challenges of neural networks. They bring in these high-dimensional dense vectors, and there could be millions of them. If we multiply the time/space costs by 100 million or even a billion, very few systems can still hold together. And additionally, training a neural network requires caching the intermediates between the forward and backward paths, resulting in serious storage blowups. It's surprising how quick RAM can be depleted during GNN training, causing many troubles. At this stage, we can make a few observations. You see, GNN challenges are actually mostly data challenges brought by the complexity of graph data processing. And data challenges require data solutions and data systems, which the popular deep learning and GNN frameworks commonly lack. On the other hand, the existing GNN systems, they have an over-reliance on the deep learning frameworks for graph processing as big matrix multiplications. I would argue that this is flaky because of the very limited GPU memory, and they run into a lot of memory issues because of that. And we will see that later in our experiments. Also, these systems, they mix the graph processing challenges with the neural network challenges, and usually ends up not doing well on one side or another. Finally, these systems are practically reinventing the wheel of years of large-scale graph processing systems research by re-implementing the very basic graph processing operators. That then leads to our work, LOTEN. Our take is that GNN equals graph processing and neural network. We divide and conquer the scalability challenges of graph and neural network separately. This is then analogous to the separation of compute and storage in cloud computing. We can then use dedicated but existing systems to tackle these challenges separately, and they can scale independently, meaning if you scale up one side, the other side doesn't necessarily get interfered because of the changes. This way, we can also bridge the gap between existing graph analytical systems with GNN workloads by enabling the user to train GNNs directly within their graph analytical system without data export, using the deep learning frameworks transparently. And hopefully we can bring the best benefits of both worlds and combine them in LOTEN. In this paper, we would then set out to answer two fundamental system questions. First is, can existing graph analytical systems bring benefits to GNN training? And how far can we go by pushing existing systems' limits without modifications to their code base? We will answer these questions with our empirical tests later. And here is the architecture diagram of LOTEN. We have the data and the user. The data is first ETL'd to the graph data system. We also have a GNN-centric graph partitioner to plug in, and it can save communications during the runtime. And the data is stored and distributed by a graph engine, which is an existing graph data system running on our workers. The user defines the GNN model using the deep learning engine's APIs. Here is another system technique called GNN model batching, which batches multiple models together to amortize the cost. And at the heart of LOTEN, we have a planner component that figures out the global computational graph and the optimizations. It turns out we can do some database style plan optimization and rewrites. The tasks are then distributed to the backend graph engine and deep learning engine, which I mentioned earlier are existing systems without modifications. Between them is a component we call messenger to reconcile and facilitate efficient data transmission between them. And that was an overview of Loten. And here is a list of the technical innovations we have in the paper. We have the query planner, the GNN model batcher, the GNN-centric graph partitioner, and many engineering efforts we put in the messenger. As you can see, each component contributes to substantial speed ups. Finally, I want to show a snippet of the experiment results. All of our experiments are done on an 8-node cluster. We tested it on multiple datasets and models. First is the end-to-end results. There are 3 other systems we evaluated: distributed DGL and AliGraph, industrial software. Sancus is a recent research project from the academia. And on the OGBN products dataset, this is a medium-sized graph from the standard open graph benchmarks. On the GCN workload, you can see Loten is faster than this DGL, but not as fast as Sancus, right? However, Loten has higher accuracy than Sancus. This is likely due to the fact that Sancus uses approximate processing that can hurt the accuracy. And also, Sancus would start to fail out of memory on larger workloads, as shown on this OGBN OGBN papers 100 million dataset. Loten is actually the only one that's still able to scale to this workload. And next up is our ablation study. This is to demonstrate the effectiveness of our techniques. To do this, we did a naive implementation of Loten, but without all of the system optimizations. We then add them back one by one. As you can see, overall, our optimizations can yield a 76 times speed up. And obviously, we have much more numbers and tests in the paper where we comprehensively tested the capabilities of Loten. We showed that Loten can indeed handle data scaling and model scaling independently, allowing for much larger models to run than other systems can do, and opening design freedom for the practitioners. You should definitely check out the paper if you are interested. So to recap, Loten does not hurt the accuracy of full graph GNN training. It's the most scalable system, and it can provide throughput gain on many workloads. We can indeed bridge the gap between graph data systems and GNN workloads, offering both better scalability and higher efficiency than the baselines. With that, I would like to stop and take any questions you may have. Thank you very much.